Okay, continuing with voltage relationships, section 8.9. Don't want to wear you out on the math on this. And like I said, we're just going to go through it one time. And, so you see where this number 1.73 is derived. And let's go back to our drawings that we were looking at earlier, figure 813, A, B, C, and D. Okay, and like what we were saying here, I've gotten ahead of us a little bit here, so you don't have to wait on me. But again, what I'm trying to figure out here, what I'm trying to derive is what the voltage is from phase A to phase B. And we're going to reference that in terms of phase A to neutral as well. Okay, so what I can do is I can write this equation for EAB. EAB is equal to EAN plus ENB. Okay, so that's what I've written there. And then I can rearrange that so that, it looks like this equation here. Now, let me do this thing here, and then we'll go through and I'll show you, the textbook solution and his way to solve this. If I took this portion, one of the phases of the three-phase phasor representation, okay? And I'm going to turn it so that EAB is here, okay? And then EAN is here. And then this minus EBN, which is just, another way to write positive E and B, is here, okay? So we know this is 120 degrees, right? We know that from our phase relationships with our phasor diagrams, right? So we know that's 120 degrees. Well, we also can determine that these two angles here are equal, so they both have to be 30 degrees. So what I'm going to do, and I was telling you this just to, I don't know, as a former math teacher at one point, I guess I felt a lot of times trying to make stuff practical. But anyway, so what I'm showing you here is an application of the law of sines, which says this side A over sine A this side A over the sine of the angle A is equal to B over the sine of the angle B, and side C here is equal to the sine of the angle opposite that side. Okay, so to put some numbers in this, the sine of 30 degrees is 0.5. The sine of 120 degrees is 0.866. And so anytime, you're working with the law of sines, if you know 3 of the 4, right, you can do that. And one of the favorite things to do if you don't have actual numbers is let's see the relationship, for a unit 1 calculation. So let's assume that line A is equal to 1. What is the relationship from side A to side B? And we go through with this. So we put A as 1 here over 0.5, which is the sine of 30 degrees, is equal to C over 0.866. Okay, and so if we solve that for C, what we get is the relationship between this side A and this side C is 1.73. So if this is 1, this is going to be 1.73. So what we can take away from that is anytime we know the phase to neutral measurement, we can multiply that by 1.73 and get the phase to phase measurement. All right, to put that in, so let me erase this here. Okay, so what that says is if I know that if I know this value, okay, then I know that this value is going to be 1.73 times more than what this value was. Okay, so that's a very interesting thing to be able to take away from here. And so another way to get there is the way that Wildy does it in the textbook, where he says, what is the length EL of phasor EAB is equal to 2 times the voltage line to neutral times the cosine of 30 degrees. Okay, because I have 2 of those, right? I have 2 of those line to neutral here, a line to neutral, a line to neutral. Okay, and I'm trying to get that length of the long side. And so I could go through this process. And so this EAB is what we call line voltage, phase-to-phase voltage. 2, and then an identity that we could use is the sine of 30, the cosine of 30 degrees. The cosine of 30 degrees, he writes it as it's equal to the square root of 3 divided by 2. Okay, and that would be an identity that we have. So if I have square root of 3, which is 1.73, divided by 2, I get this 0.866, right? Which is the same thing as the cosine of 30 degrees. So it's just another way to write 0.866. Okay, so cosine of 30, 0.866. So it's just another way to write this number. This. Now, why would I do that? Well, the reason I want to do that is if I'm trying to solve this, right, these 2 will cancel out. And so I've given that the line voltage is equal to the line to neutral voltage times the square root of 3, right? And again, we're going to get to that same number. And like I was telling you before, there's a lot of people that work in the electrical world, and they know this number 1.73, but they have no idea where it comes from, all right? So that's where it comes from, and that's a value that we're going to use. We're going to use that often as we work through these types of 3-phase problems, and it's going to be valuable to us when we look at this in some different ways going forward. Now, we got there a couple of different ways, but I just wanted to show you that and utilizing math to get these values that you're going to run into. And so here's an example in 814 that says, here's the line to neutral voltage, and I'm given that line to neutral is equal to 100 volts. If I went and I measured from phase to phase, or from phase A to phase B, it is going to be that value, E sub L, or line voltage, would be 100 times 1.73, or the square root of 3, or 173 volts. And that's what that number is there. And that's where it comes from. Now that works for, of course, each phase, because all this is symmetrical, and it all works out very well as we go through this. All right, so let me stop this, and then we'll work example 8.3, and I guess we'll do 8.4 and look at the delta configuration after we go through that part.